Hello and welcome to this video in which I will explain how to build a coaxial transmission line in MATLAB and how to analyze it, visualize the fields using the tlcalc function. I will assume that you are already familiar with building geometries in data arrays, you are familiar with transmission line theory, and also that you watched the first MATLAB session video in which you analyze a microstrip transmission line. With that said, let's begin. First, we have MATLAB. We will click here on New Script. We will write the file name. I will call this Coaxial Demo tlcalc. I will copy this and save it as the name of my file. Now that the file is saved, let's begin with the code. First, we will initialize MATLAB. We will first close all open figures. We will then clear the command window, and then we will clear all the variables. This ensures that MATLAB starts with a clean slate every time you run the code. Next, I will put some physical units that will help us build our coaxial transmission line. First, we will define meters as 1 and seconds as 1. Now, we will define millimeters to be 1 times 10 to the 3 times meters. We'll do the same for centimeters. 1 times 10 to the minus 2 meters. Now we will define some frequency units. Hertz is equal to 1/second. Then we will define gigahertz to be 1 times 10 to the 9 times hertz. Now we will define some physical constants. For now, we just need the speed of light in vacuum, which is given by 299,792,458 times meters over seconds. And finally, we will open a figure window. Now we can save and run our code to make sure that there are no errors. As you can see, here we have all our variables and the figure window. Now we can go and define a dashboard with the simulation parameters. First is the frequency. F0 will be equal to 2.4 gigahertz. Now we will define our coaxial transmission line parameters. ER is going to be equal to 2.5, which is the relative permittivity of the coaxial line. R1 is going to be equal to 0.25 centimeters, and this is going to be our inner conductor radius. R2 is going to be equal to 3.0 centimeters, and it's going to be our outer conductor radius. Now let's define some grid parameters. The first one is what I call nres, and this is going to be our grid resolution. This is the number of points or cells that MATLAB will resolve per length that we will choose later. A higher nres means a higher resolution simulation, which can lead to better results or converged results, but also it can make your simulation run slower. Now we will define our physical size of the simulation. Our physical size of the grid along the x dimension is going to be Sx, and it's going to be 8 centimeters. You have to make sure that the physical size is bigger than the size of your coaxial. Will be your physical size in x, and your Sy equals 8 centimeters, and it's your physical size in y. Now with these parameters, let's run the simulation. First save, then we'll hit run, and we have no errors, so that's good. Let's go to the next step. Now we will calculate the grid. First, we need to initialize our resolution. Our dx is going to be the physical size of a single cell of the simulation in the x direction, and dy is going to be the physical size of a single cell of the simulation in the y direction. For this, it will be the minimum value of R1 and R2. So what this function does, min, is that it will take the smallest value between R1 and R2. Here we know that the smaller value is R1, but if you have many dimension complicated transmission lines, then it's good practice that you use min to resolve the smallest dimension of your transmission line. Now we're going to divide this by nres. So what this means is that your physical cell size dx is going to be at least 20 unit cells to resolve the minimum dimension. Now we will do the same resolution for dy, so we can just copy paste. Now here's a trick to snap the grid to critical dimensions. Sometimes there is a mismatch between dx and sx and the number of unit cells, so that you are not able to resolve the coaxial transmission line in an exact integer number of cells. These two lines of code will assure you that you can resolve the dimensions of the coaxial transmission line in an integer number of cells, increasing convergence. For this, we'll define nx to be the ceiling seal of R1 over dx. This will make sure that nx is an integer and that is always rounding up regarding R1. By the way, you can choose either R1 or R2 for snapping the grid in X. Now we will recalculate our new dx as being your value of the critical dimensions R1 over nx. We do the same for ny. Now we do R2. This will make sure that you can resolve the coaxial transmission line dimensions R1 and R2 with an integer number of unit cells in the x and y directions. Keep in mind that you can only use one dimension along one axis. Now we will compute the grid size, which is going to be the number of unit cells and x and this nx is going to be equal to CL rounding up Sx over dx. We do the same for ny. We can copy paste and then we can just change the x's for the y's. Let's run the simulation again. We don't have any errors, that's good. And now we have these variables nx, which corresponds to 640, and ny, which corresponds to 640. This is our number of unit cells in the x and y directions. So your grid is going to be 640 unit cells times 640 unit cells. Now let's calculate the grid axis. These are our axes that will help us in building the mesh grid. You should be familiar with this code by now. Your x-axis is going to go from 0 to nx minus 1 times dx. And then we center the grid. Just put this as a comment, is our x-axis array. And then we will center our axis by subtracting the mean. We do the same for the y-axis. So we can just copy paste and then change everything to y. So now we have our x-axis, which is a one-dimensional array centered at 0, and we also have our y-axis, which is a one-dimensional array going from 0 to ny minus 1 times dy, and it's also centered at 0. Now we can create our mesh grid. It's going to be y x equals mesh grid ya xa. Remember that the mesh grid is the canvas in which you will build your coaxial transmission line. Treat this as if they were x and y variables of a function. Now it's time to build the coaxial transmission line. First, we will build our inner conductor. In this case is conductor 1. And remember that mesh grid y and x is our canvas in which we can build different geometries by putting them as functions. So our C1 is going to be these variables put in the form of a circle. X squared plus y squared. Remember to put the dot here so that MATLAB knows it is a point-by-point multiplication and not a matrix multiplication. This is going to be a Boolean and it's going to be less than or equal to the inner radius squared. Now let's build the outer conductor. C2 equals, we can even copy paste this same equation, x squared plus y squared, but now we change to R2 squared. We name this outer conductor, conductor 2. Now we will define the dielectric array inside the coaxial. Now this dielectric is going to be equal to also a circle with the radius set to the outer radius. So these and these are going to be the same for now. Now we can change our ER to place the dielectric material, and is going to be equal to 1 plus ER minus 1 times ER. This means that wherever wherever there is no ER, ER is going to have a value of 1, and then whenever there's ER, it's going to have value lowercase ER. Now let's visualize our arrays. You should already be familiar with this code, subplot. Again, 2 rows, 3 columns. The first plot will be image C, XA, YA, and then C1 transposed, axis equal, type, color bar, and then title C1. We can copy paste for the C2 array. Now we change it to 232, and we also do the same for ER. Let's save and run our simulation. Oops, there's a mistake. There's a typo here. This H should not be here. Now let's run again. Here we have our figure that shows the first conductor, which is the inner conductor, then the second conductor, then ER. But you notice that maybe something is weird with C2. We actually want the C2 to be outside of this circle, because if we leave C2 to be like this, it will overlap C1 and also ER, and then our simulation would fail. And also remember that C2 is the outer conductor, so it should actually be here outside. So we have to change C2 to be the inverse, right? The Boolean inverse of C2. So we will write 1 minus C2 here, see if this works, which means that it will calculate this line of code will get you the inverse of what we did with C2. And you can see that it looks better now, right? Just remember when building transmission lines that the inner conductor or C1 is actually where you feed your voltage. So it should always be C1 for tlcalc, and then C2 should be either your ground, or if it's a differential line, your negative voltage. So I think this coaxial cable looks right. Let's just make sure that if we add everything together, let's do another subplot now, 2, 3, 5, for example, and here we put as the title coaxial line, and here we will put the sum of conductor 1, conductor 2, and ER. Let's see how they look together. I think it looks good. We have ER, which is 1, and then 2.5, and then C2, which goes from 0 to 1, and then the minimum value here outside should be 1 and 1. Should be equal to, and then the value here inside the coaxial should be ER, which is 2.5, and then our C1, when we add everything together, should be 1 plus 0 plus ER should be around 3.5. So this is just a method that you can use, like adding everything up, to see if your coaxial cable, when you overlay everything together, it looks fine. So I think it does. Let's just comment this by selecting. You select and then you click Ctrl R. Now we are ready to simulate our transmission line. We will run tlcalc, and then here we will have our output parameters, characteristic impedance, the index, inductance, capacitance, voltage, our fields in X and our fields in Y, and we call the function tlcalc, and we feed the function the dielectric, conductor 1, conductor 2, dx and dy. Let's see that we have everything in order by running. Hopefully there's no error, and there's no error, and we have now some parameters here. We have L, we have C, we have N, so I think this looks okay. Now that we run tlcalc, we can calculate our propagation constant by using the N we got from tlcalc. Let's do this first by calculating the wavelength, free space wavelength, which is C0. Remember that we put the physical constant, the speed of light, over the frequency. Then our k0 wave number equals 2 times pi over lambda naught. And then our beta is equal to k0 times n. Now we are ready to report our results. We'll use disp, then we will put the text z0 equals number to string of characteristic impedance z0 ohms. We can copy and paste to get beta, and it's going to be our num2 string of beta times centimeters, and the units of beta are radians per meter. Let's put a space here. We can copy and paste again. Now for n, our effective index, which is unitless, let's display the inductance, num2 string L, which is henries over meters. This should actually read, shouldn't be centimeters, so that would be let's put meters, because we have here radians over meters, right? Finally, we display C, num2 string C, and then the units are farads per meters. Let's run this. And here you go. We now displayed our results. And it seems that everything is working fine. Now, the final step will be to visualize our fields. We'll take advantage that we already used the subplot here, 1, 2, 3, and then use 4, 5, and 6. We can go to our previous subplot lines of codes, then just copy paste it and use it to show. Now we'll show the voltage V, so we'll put V here. We'll display our voltage. We copy paste to show the electric field in X, and then same thing with the electric field in Y. Now we are ready to run the code, and oops, I didn't change the subplot of EY to 6. So now let's rerun, and you can see here that we have our nice plots of our inner conductor, our outer conductor, the dielectric, the voltage. If you see here in C1 is where tlcalc applies the voltage, where it feeds, and then C2 for the option of regular transmission line that is not differential, it will force all the fields, the voltage in C2 to 0. So that's why you see here at C1 we have 1, and then it goes down to 0 as we approach C2. And this is what the voltage of a coaxial transmission line should look like. And also we have our EX in volts per meter, and then EY also. So here you go. This was the video for a MATLAB session to how to build a coaxial transmission line and how to analyze and visualize the fields using tlcalc. See you guys next time.